Good afternoon, everybody, and welcome to this IMechE webinar by MAHLE Powertrain, titled Innovative Engineering for the 21st Century. My name is Robert Morgan from the University of Brighton, and I'll be chairing today's webinar. Today we have presenting James Taylor, who is the Chief Engineer of the Analysis, Development and Optimisation Department at MAHLE. We then have Dr. Mike Bassett, who is the Chief Engineer in Research and Advanced Engineering. We then have Christian Worth, who joins us from MAHLE GmbH. And finally, Dave Apatz, who joins us from MAHLE in the US. So before I hand over to our presenters, just a couple of points of housekeeping. So first of all, I'm sure you know this from all similar events, please keep your mics on mute. Second, you can post questions at any time during the event, so even when the presentation is running via the questioning feature, and those will be picked out in the Q&A session. And finally, we'll be recording the Q&A session and providing recording to the attendees after the event. So that's all for me, and I'd like to hand over to our hosts at MAHLE.
Hello, welcome to MAHLE Powertrain's webinar on innovative engineering for the 21st century. In this presentation, we'll showcase the breadth and capability of our engineering services that we provide to our customers and how our skills and capabilities that we've honed in the automotive sector have been successfully applied to non-automotive projects, which have been a key to our success in the 21st century. First of all, a short introduction to MAHLE Powertrain. We're a global organisation with sites in the UK, US, Germany, Brazil and China. This presentation will be given by myself, James Taylor, and Mike Bassett from the UK, Mike Bunce, who's Head of Research in the US, and Christian Worth, who is Head of Transmission Engineering at MAHLE ZG in Germany. MAHLE, our parent company, is a major Tier 1 supplier to the automotive industry, manufacturing engine components and thermal management systems. Recently, MAHLE has also made significant steps into the electric propulsion area, following acquisitions and investments in e-motor and power electronics companies. MAHLE Powertrain is a wholly owned subsidiary of the MAHLE Group, and from our locations around the world, we focus on supplying our customers with world-leading engineering services. Over the last 10 years, MAHLE Powertrain has been developing capabilities to enable us to support our customers with their hybrid and full electric propulsion systems, from bespoke transmission and battery packs to electric motors and power electronics. Whilst we focus on design and development of advanced vehicle propulsion systems, we also offer support to our customers for any part in the process, including the provision of prototype manufacturing. I shall now take you through our core competencies. In design, we use our engineering capabilities to lay out designs for battery modules and packs, design high-performing internal combustion engines from clean sheet or as performance and emissions upgrades. We also design transmissions, e-axles and e-motors. We have a reputation for delivering running hardware to tight timescales, with many examples of hardware in less than 9 months. In analysis, we have a strong team using a combination of 1D, 3D and thermofluid toolsets. We also have specialist gearbox and driveline software for analysis and optimization of transmissions. In development and testing, we have a lot of experience in hardware selection, development and validation. We're specialists in combustion system development and optimization processes, which are focused on meeting stringent future emissions standards. This development capability is complemented by our well-resourced facilities, which include battery testing, internal combustion engine dynos, e-axle and transmissions rigs. We also have our real drive emissions centre for testing vehicles under climatic conditions, which is a key part of our RDE process. In calibration and controls, we are very experienced in base engine optimization and base vehicle calibration. We're also experienced in developing demonstrator vehicles for performance upgrades and for newer technology assessments. Our tools and core competencies have allowed us to deliver exciting automotive projects. This is just a selection of high-performance automotive programs that we've been involved with over recent years. They include high-specific output internal combustion engines, novel combustion systems, transmissions and complete powertrains. So who are we and where do we come from? We're a team of talented people committed to creating innovative and sustainable solutions for our customers. MAHLE's Powertrain can trace its root back to the foundation of Cosworth in 1958. and in 1986 it put its first engine into production, the Ford Sierra Cosworth. In 1998, the road car division of Cosworth was acquired by Audi, creating Cosworth technology. Then in 2005, MAHLE purchased Cosworth technology from Audi and created MAHLE Powertrain. So MAHLE Powertrain has been active in the automotive sector for over 60 years. During this time, our talented engineers have developed their skills in a broad spectrum of disciplines ranging from fundamental research, concept design, modelling, analysis and simulation, through to prototyping, testing, calibration, software development and systems engineering. These toolsets, coupled with our in-house developed tools and techniques, have also been successfully applied across multiple non-automotive sector projects to provide technical solutions for our ever-increasing range of customer projects. In this next section of the presentation, we're going to take you through a selection of example projects showing how MAHLE Powertrain has diversified from our core automotive powertrain activities, delivering solutions into different areas, including renewable energy, aerospace, medical, off-highway, stationary power generation, and e-mobility.
The fast-changing legislative emissions and efficiency requirements for vehicle powertrains pose significant technical challenges. We've been developing innovative solutions to meet these requirements for future sustainable powertrains. During the past decade, the pace of this change has quickened and led us to develop a host of new capabilities and skills which we want to showcase today. Furthermore, we want to show how MAHLE Powertrain are able to support our customers to overcome their technical challenges. Nowadays, we're all familiar with the concept of the electric vehicle, which is powered by an electric motor, and the sole source of energy to propel the vehicle is provided by a battery pack. 10 years ago, when we began our range extender project, the typical range of an electric passenger car was only around 80 to 250 kilometres, or 50 to 150 miles. The range of vehicles was limited by the large size, weight and high cost of the battery. The idea of the range extender is that by the addition of an onboard generator, which could convert a liquid or gaseous fuel into electricity, the battery pack can be charged whilst the vehicle is moving. This enables the battery capacity to be optimised to the capacity that's needed just for typical daily use. And then for longer or infrequent journeys, the vehicle can be refuelled using existing conventional infrastructure, and the driving range is effectively limitless. As an initial step into hybrid and electric powertrain technologies, at the beginning of 2010, MAHLE Powertrain set about designing an engine specifically for use as a range extender. We undertook a concept study, produced the final design, and built the running prototype in under 12 months. The range extender engine design has been focused on meeting the requirements for a small to mid-size passenger car. During the concept phase of the project, key attributes for the engine were identified, and the resulting design has been targeted to achieve a very compact design with low weight and a low manufacturing cost. To minimise size and weight, the axial flux generator is fully integrated into the crankcase of the engine, with the rotor mounted directly onto the crankshaft of the engine, like a conventional flywheel, without any separate bearings. To maximise the flexibility of installation and to maximise commonality across a range of applications, the unit can be installed either vertically or horizontally, using the same major castings. Detailed vehicle analysis was performed to determine the required specification for the range extender. A wide variety of technologies were considered during the concept phase, including both 2- and 4-stroke engines and rotary and gas turbine engines, amongst many others. The project developed MAHLE Powertrain's capability in the design and testing of high-voltage electrical components and our capability to test high-voltage traction motors. In 2012, we undertook the design and development of a prototype range-extended electric vehicle as a showcase for our range extender engine. This also served to further develop our skills and capabilities in vehicle electrification. We undertook the complete vehicle conversion in just 9 months, including the development of the vehicle control system and full vehicle calibration. We developed a GPS-based control system that used prior knowledge of the energy required to travel over the route, along with vehicle speed and gradient data to determine the optimum operating strategy for the range extender. This delivered a fuel saving of over 5% compared to a purely reactive strategy based on instantaneous vehicle speed and battery state of charge alone. The vehicle and engine have been developed to have excellent MVH, with the engine operation being barely perceptible to vehicle occupants. Additional features include a battery thermal management system that can control the battery temperature in hot and cold ambient conditions using the vehicle air conditioning and heating system. The analysis and development of the thermal systems was all done in-house using our detailed vehicle models linked to our thermal modelling tools, which can accommodate multiple coolant loops and AC circuits. All aspects of the vehicle conversion were undertaken in our in-house workshop facilities. We started with a conventional gasoline-engined vehicle with manual transmission and removed the powertrain, and then installed the complete high-voltage system and traction motor and our range extender unit. New capabilities include the capability to undertake the design and integration of the high-voltage systems into a vehicle. We developed a flexible hybrid and electric vehicle control unit that has been subsequently used to enable rapid development of other complex prototype vehicles and also to control other complex systems. It has also given us detailed MVH and cooling system capabilities, ranging from analysis through to prototyping and complete system development. Recently, we have updated our range extender concept to meet the requirements of vehicles for 2030 and beyond. The MAHLE Modular hybrid powertrain features an updated, dedicated hybrid engine design that achieves very high levels of brake thermal efficiency using a combination of cost-effective technologies. The port-fueled gasoline engine uses a novel pre-chamber combustion system we call jet ignition, or MJI. My colleague Mike Bunce will talk in more detail about this later. This system enables us to operate with a high geometric compression ratio and tolerate high levels of exhaust gas recirculation to achieve the high efficiency from the engine. The modular hybrid drive system can be configured to enable it to suit a wide range of vehicles through a modular transmission design, which can operate in series or hybrid drive modes. The transmission can be configured with 1, 2 or 4 gear ratios, depending upon the vehicle application requirements. The engine can be configured in 2 or 3 cylinder formats, and the power of the traction motor can be varied. These levels of flexibility enable the concept to be tailored to meet the requirements of a wide range of vehicles from 1,000 kilograms curb weight through to very large SUVs of 2.5 tons, whilst retaining maximum component commonality. The project further enhanced our capabilities to fully integrate high-voltage components, as illustrated by the transmission unit shown, which features a fully integrated generator and traction motor, leading to new techniques which we have developed to optimize and streamline our design, analysis and validation processes for these types of devices. MAHLE's Efficient Electric Transport, or MEET for short, is the vehicle concept for tomorrow's urban mobility. The target was to develop a 48-volt highly efficient vehicle optimized to meet the requirements for city driving. The vehicle is also intended to be a showcase for our parent company's e-mobility products. The MEET car features a twin-motor drive system where each motor drives one of the rear wheels independently and features a 15 kilowatt-hour battery pack, which can deliver 60 kilowatts of electrical power at only 48 volts. The use of a 48-volt powertrain is estimated to reduce production costs for the traction motor and power electronics in production by 25%. MAHLE Powertrain were responsible for the design of the transmission and traction drive system integration, as well as the vehicle build and development. We also used our flexible vehicle controller to enable the development of the vehicle to be achieved in a very short time frame.
MAHLE Powertrain has experience developing micro CHP systems for power generation. We developed this capability through a project that we had funded by ARPA-E, which is a division of the U.S. Department of Energy through their GenSets program. The objective of this program was to develop a high efficiency, low emissions, long life 1 kilowatt micro CHP genset, and it was to be used for permanent residential power and heat, and it was meant to be supplementary to the grid. Some of the project partners on this project included Kohler and Oak Ridge National Lab. The concept that we proposed was a natural gas fueled, very high stroke to bore, low friction, clean sheet engine design. This engine operated ultra lean for increased thermal efficiency. We also incorporated high efficiency heat extraction components on this engine and also used low temperature aftertreatment to meet the emissions requirements. You can see an image of the engine in the upper right, and then in the upper left is a diagram of the complete system that we were developing. The results of this project were that we developed multiple engine families, one a single-cylinder 1 kilowatt engine, and then a 2-cylinder family of engines from 3 to 10 kilowatts. All of these engines exceeded their thermal efficiency targets. You can see the chart on the bottom right shows that our 1.5 kilowatt engine achieved a peak break thermal efficiency that was an increase of approximately 20% over current state of the art in the 1 to 2 kilowatt size class, and this was done at a 50% reduction in cost versus its closest competitor. We used some of our core competencies at MAHLE Powertrain to execute this project, but the project also allowed us to diversify those competencies at the same time. On the design side, we designed a base engine, and we took a systems approach to designing this engine as well. It was a clean sheet engine design, which we have experience with, but we've never really used it in the context of a system design that had so many competing interdependencies. So for instance, when we were looking at an engine that generated a very high degree of thermal efficiency, the heat extraction of the engine would also suffer. So the CHP portion needed to really be in balance. In order to do that, we had to diversify our design capabilities so that we could manage all of the system interdependencies. On the analysis side, we developed a system efficiency prediction utilizing some of our existing analysis expertise. The model that we developed incorporated empirical data, 1D analysis, and CFD analysis, and we used this to provide an initial prediction of the efficiency of both the engine and the system. This model, in turn, was used to help guide the specification of the individual subsystems, including the engine, and from that specification, we then generated requirements and initial conditions for the subsequent refinement of those subsystems. So we're using our analysis capabilities that we have existing, but we're able to diversify how we use analysis and how we generate boundary conditions for an entire system. The development side, we have engine and system testing experience, but in this case we had to develop an engine dyno that was capable of providing very high resolution efficiency data from a single cylinder engine, which is a notoriously difficult thing to do. So we developed an engine and dynamometer system that gives us this very high accuracy on the efficiency data that we're trying to track. We also incorporated iterative flow bench reactor and engine testing to be able to develop the advanced lean aftertreatment package with Oak Ridge National Lab. MAHLE Powertrain has experience in the area of alternative fuels. One of our most recent projects was a commercial program with an OEM. The objective of this project was to develop a safe, stable, hydrogen-fueled combustion system for heavy-duty off-road applications. Hydrogen is a fuel of interest in the European Union currently due to its classification as a zero-carbon fuel. The challenge with hydrogen fuel is that it is highly prone to pre-ignition and to knocking due to its low auto-ignition temperature. In heavy-duty applications with large bore sizes, this problem is exacerbated by the long travel distance associated with heavy-duty operation. The concept that we proposed was an ultra-lean heavy-duty engine operating with the MAHLE jet ignition, or MJI, combustion system. This is a pre-chamber-based combustion system that provides a significant lean limit extension versus a spark plug. And you can see from the plots on the right, extending the lean limit is a very effective tool for mitigating knock and pre-ignition. The results of this approach gave us successful combustion at lambda values greater than 3, so a very lean operation, and this enabled a higher compression ratio to allow us to increase efficiency of the system. The design competency required to execute this hydrogen combustion program involved modification of existing production engine platform. In this case, we redesigned the cylinder head to accommodate the MJI components. On the analysis side, we had two key areas of analysis that we needed to focus on. The first was correlation of knock models across multiple analysis formats. So because hydrogen combustion is very prone to auto-ignition and pre-ignition, we had a requirement for very high resolution knock and pre-ignition prediction. So to do that, we utilized 0D, 1D, and CFD knock models, and we developed a methodology to correlate the knock modeling across those three packages so that we could use each of the three packages to further guide development of the combustion system. Also on the analysis side, we had to develop a high-resolution CFD analysis. This was because the fuel chemistries associated with hydrogen combustion are fairly complex, and of course, hydrogen molecules are very small, so this tends to present a challenge for tracking fuel diffusivity. So we needed to develop a CFD modeling approach that was able to capture the behavior of interest while also balancing this resolution with computational intensity. We applied these competencies and the diversification of these competencies to hydrogen combustion. We are also working with a variety of global partners in the area of ammonia combustion system development, and we are applying the same tools to be able to accomplish that.
Another good example of MAHLE Powertrain's diversification is the MAHLE Stirling engine. This represented an investment in zero carbon power generation with electrical energy generated directly from the sun. MAHLE Powertrain designed and developed the first concept demonstrator engine running on the testbed in 2011. In early 2012, the targets for performance and efficiency were exceeded, an example of true first principles understanding and a fully integrated engineering system approach. MAHLE's first clean sheet Stirling engine presented many challenges. As we were starting from a clean sheet, all the components needed to be evaluated from first principles. The project utilised literature research, established automotive techniques, and new simulation methods. As an example of where our automotive analysis techniques were applied was in the creation of a highly detailed 1D thermodynamic performance model. This was used to lay out the basic engine geometry and optimise the sweat volume. It also allowed many hardware combinations to be assessed, allowing rapid refinement of the concept. In order to confirm the performance and efficiency of the prototype Stirling engine, our automotive internal combustion engine test facilities were modified to allow safe engine and rig testing. This included commissioning of the hydrogen safety systems and construction of a gas burner to replicate the sun. Through this project, MAHLE Powertrain gained theoretical and practical experience with the Stirling engine machine.
Modern wind turbines are characterized by high mechanical and high aerodynamic efficiency. While the mechanical efficiency is significantly influenced by the losses in the transmission, the aerodynamic efficiency also depends on the diameter of the nacelle in relation to the rotor diameter. The aim of the transmission is thus to be able to support high rotor torques with a small transmission diameter. In practice, this is achieved through the use of planetary gears, which can achieve a high power density through their internal power distribution to several planets. The planetary gear, which has to support the rotor torque, is naturally the most heavily loaded. Gear topologies in which the rotor torque is supported not only by one but several planetary gears can have significant advantages in terms of power to weight ratio. In a study for a wind turbine manufacturer, all capable gear topologies up to 4 planetary gears were systematically determined. The self-developed transmission synthesis program PlanGear was used for this purpose. PlanGear determines and evaluates all transmission topologies with full computer support. The weight and efficiency of the transmission system were mainly used as evaluation criteria. In the end, the result was a handful of gear structures that, compared to today's known transmissions, have the potential for a higher power density and a smaller outside diameter. However, it is not only the transmission topology that has a strong influence on the efficiency of the wind turbine, but also the losses in the individual gear meshes of each gear stage. The efficiency of a gear mesh always has a conflict of objectives with regard to lifetime and noise of the transmission. While MAHLE Powertrain uses the in-house developed synthesis program PlanGear to select the optimal transmission topology, a large number of tools are used to optimize the design. Here, exact calculations are only possible if you not only consider individual components, such as gearing, but the entire system. MAHLE Powertrain uses, for example, software packages such as Master or PERMAS for system and component analysis. With the help of finite element analysis, precise stress calculations and lifetime predictions can be made. Detailed analysis for vibrational excitations from gears also carried out, taking the overall system into account. Vibrations can be decisive for lifetime and strongly influence the noise behavior. Another project was an aviation project. Here, a so-called flight rotary actuator was optimized. The landing flaps on the wing of an aircraft are operated with the aid of the transmission using a very high gear ratio. A motor drives a master shaft that runs almost along the entire wing and operates the flaps via several flight rotary actuators. Those consists of a bevel gear and a so-called Wolfram planetary gear. A Wolfram gear has the great advantage of being able to provide a high gear ratio and a high load capacity with a very low weight. The disadvantage is the relatively high losses that are inherent in them. In a research project, MAHLE Powertrain optimized the Wolfram planetary gearbox. The Wolfram gear consists of a driven sun gear that meshes with the planets. The planets on the carrier mesh with 2 ring gears that have a slightly different number of teeth. While one ring gear is fixed via the housing, the other ring gear drives the linkage of the landing flaps. The carrier rotates freely and is not connected to outside. To optimize the Wolfram set in terms of load capacity and efficiency, the gear meshes of the planetary set were revised and the planet carrier redesigned. The tooth forces generate large tilt torques on the planets, which normally lead to larger displacement on the planets in relation to the ring gears. This leads to a poor load distribution along the face width of the gear meshes and hence to a wasted load capacity potential. In addition, with the usual gear designs, decisive losses occur at the tooth meshes. As part of a research project for the transmission supplier, MAHLE Powertrain developed an optimized design for the Wolfram gear. For this purpose, the starting point was first analyzed in detail in order to identify optimization potential. With an innovative gear design, the transmission losses could be significantly reduced. However, this new gear design needs an improved load distribution along the gear meshes to meet the required load capacity. This was achieved using a new type of carrier design with significantly increased stiffness. Now, the tilting torques on the planets are not balanced by radial bearings, as usual, but by axial bearings. Overall, this results in significantly lower deformations, keeping weight constant. Finally, the transmission losses could be significantly reduced without having to accept disadvantages in terms of weight and load capacity.
48-volt mild hybrids can match the fuel-saving benefits offered by higher voltage hybrid vehicles. Due to the reduced electrical system safety risks, there are cost benefits to using a lower voltage hybrid system. However, depending upon the vehicle size and hybrid architecture, up to 20 kilowatts electrical regeneration capability is required to maximize the fuel savings. But only a very small energy storage capacity is required. Having a low storage capacity reduces the size, weight, and cost of the battery pack, but achieving a high power from a low capacity battery pack can be challenging. As a showcase for our capabilities, we designed a high power, low capacity pack optimized for 48-volt mild hybrids. We undertook very detailed thermal and electrical flow analysis, supported by extensive testing, to optimize the design of the bus bars and cell tab welding patterns to minimize electrical resistance and temperature buildup within the pack. We've tested the pack in our facilities in Northampton and achieved charge and discharge levels of up to 20 kilowatts for over 10 seconds and can operate at power levels of 10 kilowatts continuously. This project has developed our capabilities in the detailed design and analysis of battery packs and our testing capabilities for cells, modules, and complete packs.
Another opportunity to apply our tools and processes came in March 2020 with the coronavirus pandemic. On the 13th of March, Team Consulting was approached to partake in a UK government-led consortium of technology consultancies who were given the task of producing tens of thousands of new ventilators within just 4 weeks. This requirement was in response to modelling which suggested that the NHS intensive care unit capacity may not be sufficient for the number of patients requiring ventilation support. With a clear design direction established and multiple proof of concept prototypes on test, Team Consulting approached MAHLE Powertrain on the 24th of March to discuss how simulation could assist with de-risking their design. The brief was to construct a 1D model of the ventilator and patient lung. This model could then be used to assist with specifying components, performing sensitivity studies, and characterizing system performance prior to approval testing. MAHLE Powertrain was able to react very quickly to the call to help, with the first full simulation being operational in just 3 days. This rapid turnaround did not happen by chance, as we already had extensive mechanical simulation experience. The ventilator required the simulation of several different valve types. Valve simulation is a routine part of automotive simulation, for example in fuel and oil systems, and in dedicated hydromechanical models. Typical losses and clearance were applied through experience. Air and oxygen mixture is a key aspect in the operation of a ventilator, and we already have experience in fluid mixture simulation from our work in the automotive sector. Mouthpiece and lung models were a novel aspect of the simulation, and these were generated by building on existing simulation experience. Deep knowledge of the software made this possible in the given time, and this is all done via home working with no face-to-face meetings. Innovation is a key part of being an engineering consultancy in the 21st century. In this presentation, we've shown how MAHLE Powertrain has adapted to changing demands and how it has used skills and tools honed in the automotive sector to solve engineering challenges in other industries. Thank you very much for joining us today.
Okay, thank you, everybody. I'd like to thank our... Sorry, getting a bit of echo there. Okay, I'd like to thank our presenters on behalf of everybody for that really interesting presentation, and we'll just move on to the Q&A. So I have a couple of questions to get things started. So I think, well, perhaps going directly to the question, is MAHLE Powertrain still developing internal combustion engines?
Yes, Dave Pates, Engineering Director at MAHLE Powertrain. Yes, in short, we are still developing internal combustion engines. They're obviously not dead yet. There's a life until at least 2035 and beyond. As if you take the UK as an example, where hybrids will continue to be legal until 2035 and beyond in other markets. So there's still a lot of development to be had in internal combustion engines. And of course, Euro 7 emissions coming. There's a whole load of work around combustion system development and the calibrations and after treatment systems that go with that. But of course, there's a lot of customer interest in some of the technology that we've presented today. Things like jet ignition and the alternative fuels, low carbon fuels. They will have a role in creating a sustainable future, we believe. When you consider full life cycle CO2, some of these hybrid powertrains with the correct fuel and energy generation are just as green as a BEV in some markets.
Great, thanks. And the next question we have is, which non-automotive sectors are you moving into, or with you?
Hello there. Yes, it's James Taylor here. I'll answer this one. So we've got quite a range of skills as we presented today within the business. And MAHLE Powertrain is an engineering consultancy. So we're basically looking at sort of diversification. We have been for a number of years, and we're diversifying principally into areas which are related to where our skills lie from the automotive sector. So in power generation and defence and marine and off-highway. Those related sectors are the ones that we're sort of diversifying into. But as an engineering consultant, we have a range of skills to offer, so we're open to all sorts of engineering challenges.
I think just following on from that is what are the key resources do you apply to tackle those diverse challenges?
So we've got a range of skills, as I said, and we'd deploy our first principles understanding of the engineering system. With sort of our base analysis techniques, and then we can deploy more complex analysis techniques, as we've shown during our presentation, which many of these skill sets have been built up on various automotive projects. And then we've also got the skills and resources based around our testing and development of engineering solutions for different markets. So you see how we adapted our automotive facility to work with a Stirling engine, for example. Then we'd use those resources as well to tackle those problems.
Yeah, and that follows on nicely to the next question. Really, could you give an update on the Stirling engine? On what's the latest status?
Well, the Stirling engine project, which was a MAHLE clean sheet project that we did back in 2011, 2012 time, we achieved a gateway with that. We actually achieved what we believe to be the highest efficiency Stirling engine recorded at 43% on that. But at the time, the economic situation was changing in the renewable sector, with photovoltaic cells becoming cheaper. So at the end, the concept reached that prototype phase, and proof of concept was achieved. But it was bookshelved at that point. But it is a concept that we do use and we can offer to interested people.
Yeah, it's really interesting. And you talked a bit about the modular hybrid powertrain, and what are the next steps with that?
So that for us was a showcase project where we could demonstrate our capabilities, the sort of full suite of capabilities from analysis of requirements through to the detailed design of the components and the internal combustion engine technologies as well as the electrification technologies. So for us, that was a really powerful marketing tool. And similarly to the Stirling engine, it's a potential product that we could further develop for interested parties. But really, it's our view of future automotive technology and showcasing the services that we can offer to people in that market.
Okay, yes. And finally, got one that's a bit close to my own heart as a rider of an e-bike. Are you doing anything in that area with e-bikes?
So yeah, excuse the pun, but we're peddling a range of products and technologies. So our parent company, MAHLE, obviously produces components, and they're producing e-bike traction drive systems. As MAHLE Powertrain, we're helping to engineer those products from the electric machines through to the gearboxes in them.
Yeah, you can see there's a huge number of those we're seeing on the roads around us now. They're really taking off. Okay. We've got a couple of questions from the attendees. So the first one is from Kenneth Ball. So why is hydrogen combustion complex? Seems as a simple reaction as you can get.
I'll take this one. This is Mike Bunce from the U.S. So obviously the hydrogen molecule itself is about as simple as you can get for a fuel. But the reaction mechanism for hydrogen in CFD is sort of an active area of research trying to define that and define all the chain branching reactions. So it makes simulation of that fuel combined with the very high fuel diffusivity. It makes it a challenge to be able to simulate it accurately.
Yep. And then we've got one from Owen Jones, and it says you've mentioned high compression ratio and lean lander a couple of times in order to achieve high efficiencies. Does this create any issue with NOx emissions, and how could you mitigate that?
Right, so that's a good question. So it really differs by market. So if we focus on high compression ratio, lean air dilution concepts for passenger car, there's typically no lambda that we could really get to that would be able to satisfy all NOx requirements without some form of lean after treatment. We do have some research in that area trying to optimize a lean NOx after treatment package for lean combustion concepts. We have some advantages versus the nearest analog, which would be diesel combustion. We tend to get much lower engine out NOx levels at a higher exhaust temperature than we do for diesel engines. So if we take existing diesel lean after treatment packages, we have the opportunity to optimize those quite a bit and take a significant amount of cost out of the systems. So that's how we answer that question for light duty pass car, for some heavy duty markets as well. When we start looking at small engines or stationary power, we do believe that there's an opportunity to be able to operate those engines in a final calibration, potentially without the need for after treatment to handle NOx emissions.
And from Alan Dixon, with reference to e-cars, what voltage do you mean by high voltage?
Okay, so in the auto industry, there's a standard that's been agreed by a number of German vehicle manufacturers known as LV148, and that sets a level of 60 volts as being the safe handling limit. So below 60 volts, you don't need to insulate the terminals and it can have exposed bolted joints on the electrical system, and above that threshold then you need to have an isolated system where users and people can't accidentally touch the electrical system. So that's really your threshold voltage, and as you step from below 60 volts to above 60 volts, you increase the complexity required for the safety systems.
Yeah, interesting trade-off. And next we've got another one from Owen. Another good question here is, aside from hydrogen, have you looked at any other renewable fuels, and which one do you think are the most promising?
Yeah, we're researching a range of fuels. We see, I mean, there's people working on fully bio-gasoline, which could be a drop-in fuel with the existing fleet. We see hydrogen as being a potentially interesting fuel in some markets. Certainly for marine, we're looking at ammonia as a potential fuel. I think ethanol and methanol as well, derived from bio sources, are also very interesting. And the more you refine the fuel away from something like ethanol or methanol, you lose energy content. So I think they possibly have an interesting long-term future. They're from an engine perspective, they're attractive fuels because they have a very high run number, so we can run with high compression ratios and that kind of thing. So there's a range of fuels we're looking at, and it depends very much on application and market as well. Certain fuels are more popular in different regions, depending on the available sources of energy or biomatter to generate them.
Yeah, that's sort of came out with the recent IMechE report. Yeah.
Yes.
We've got a question from we've got a question from Howard Whitaker. So do you see a continued market for range extenders, or do you think the improvements in the charging network will overtake them? And I suppose I'd also like to be interested in your comments on the 2030 ban on ICE, and do you think that includes range extenders as well?
It's a good question, and certainly for certain applications, range extenders I think have got a future. One of the big carbon burdens of electric vehicles is large battery packs. You end up encapsulating or generating a lot of CO2 during the manufacture, and actually having a smaller battery pack in the vehicle that can allow you to do the majority of driving can give you a benefit even over lifetime. And we see range extender as being a technology that enables you to make more use of the battery that you've put into a vehicle. So rather than buying a vehicle with a battery that's 2 or 3 times the size that you're likely to usually need for the occasional journeys you do of a greater distance, it makes more sense to buy a vehicle with the right size battery for your daily driving, and then occasionally use a small engine as a backup generator. So yes, I think that there is a long-term future. A range extender will be classed as a plug-in hybrid, so certainly is okay until 2035 under the current proposals by the UK government. Whether we'll see this kind of technology beyond then, I think so. I guess the ban at the moment is couched around gasoline and diesel. So whether biofuels will also be banned around that time, I think is still something that's up in the air. I don't know if any of my colleagues want to step in and comment on that.
Yeah, I think within other markets there's a more of a sort of holistic view on what's happening with propulsion systems. And I think that we'll see sort of the range extender solution and those kind of hybrid powertrains being with us for quite some years to come. I think in places such as Japan and China, where they're forecasted that those kind of powertrains will be around with us until middle of the century, for certain.
Yeah, so interesting times. Still, there's still a lot of debate in that area, and I think. A good question here from Laura Dixon, really looking at range extenders in other sectors. So, do you think range extenders are also useful in the heavy goods vehicle bus sector to increase range, or are there other solutions you think are more applicable?
Yeah, I think certainly it makes sense in that kind of application where you've got a very large vehicle, but by virtue of the usage profile, the speed profile typically driven by a bus, particularly an urban bus, the actual mean power requirements aren't ever so high. So you can have a kind of a relatively modest powered generator that's running a high duty cycle, propelling a very heavy vehicle. And I guess the competing technologies for this sort of application are the fuel cell, which at the moment are much more expensive. Clearly, this will probably change, but certainly in the short to medium term, an IC engine-based generator, be it running on conventional fuels, liquid alcohol fuels, or even hydrogen, could be a very strong competitor to that. And the efficiencies that we're starting to see, especially with the jet ignition system and the system Mike's been talking about, are approaching the efficiencies that we see from fuel cells. So with dedicated hybrid engines optimised for single point operation, we can achieve a very, very high system efficiency.
Yeah, it's interesting, and I think that came through on the recent Automotive Council roadmaps when you looked at there was a new fuel cell roadmap there, and it was interesting. The high efficiency engines were sort of in the same ballpark as the fuel cells. Next question we've got is from Nick Stiddard. And has there already been any consideration for using 48-volt batteries for household solar generation? So I suppose that's adding a battery pack to increase the amount of solar energy you can use in your house.
Yes, I think the solar systems typically run at a low, what we'd consider to be a low voltage level. I guess the pack we showcased in the slides was very much tailored towards mild hybrid applications. So it's very much a power pack rather than an energy pack. And for a solar application, you'd want the energy storage capacity rather than the high power capability. But yes, yeah, definitely a way forward to maximise the benefit from a solar system is localised energy storage.
Yeah, and it's interesting that talk about that crossover there. I mean, I've recently looked at putting solar energy into my house, and the battery costs were about 10 times what you'd expected for an automotive battery. So potentially some crossover there to get the costs down.
That's quite surprising, because I'd have thought it'd be the sort of application that would be crying out to use second life cells.
Yeah, where the mass is not really the challenge.
Yes, yeah, and it's interesting. You get about the same multiplier if you look at an e-bike battery as well.
I guess for some of those we're looking at the leisure market, and that generally attracts a premium.
Yes, yeah. So I suppose I use mine for commuting. Okay, we've now got a different direction. Now we're looking at analysis. So we've got a question here: is what FEA tools are being used for the analysis you do, and what simulations, and how good are you finding simulations now matching actual performance?
Yeah, so for FEA we principally use Abacus, but we've got a very experienced team who've used a range of tools over the years. So we're kind of used to using a range of them, but Abacus is our principal choice. In terms of how good the correlation is, we work very hard in order to achieve that, because we're using it as a tool to solve engineering problems. So we quite often will have to correlate to a particular issue that the customer presents us with, and in order to demonstrate and understand the failure mode, and then we use that tool alongside any design changes in order to validate it before actually moving to hardware to perform the durability validation. So yes, we do get excellent correlation, and you have to in order to solve the engineering problems that we have.
I think as well, it's probably worth mentioning, because of our background in terms of high performance internal combustion engines, actually the engineering challenges and the temperature levels, pressure levels, and mechanical loads that we see in sort of reciprocating components, example being the piston in an internal combustion engine, is quite a challenging environment. So when we transition to look at other engineering problems, for example a battery pack, the thermal loading, the mechanical loading actually is relatively modest for us, and we find our tools and our approaches adapt really, really well.
Yeah. And got another question here back onto hydrogen. That's obviously very topical. So real question is how do you control the flame propagation, I suppose the flame speed in a hydrogen internal combustion engine?
Sure, I can take that one. So flame speed for hydrogen, of course, and for all fuels, scales very well with lambda. Or air-fuel ratio. And for hydrogen, that's fairly important. I'd say probably most of the hydrogen combustion research that exists nowadays either focuses on very high levels of air dilution. Some of them focus on EGR dilution as well, but I don't think there's much, if any, work on lambda 1 non-dilute work with hydrogen, just because the flame speeds are too high, and you end up exceeding max rate of pressure rise requirements. So adding dilution is a very effective way to control flame propagation.
And then we've got a question from Simon Porter, sort of really extending really from that last question is what do you think the possibilities are of converting existing sort of petrol and diesel cars to run on hydrogen, and really with the view that, you know, obviously if we can make that conversion, then we generate less waste from scrapping potentially good vehicles and having to manufacture new ones.
Right. So I think there is the possibility of doing that. When we focus on hydrogen combustion, we're not looking at dedicated engines for that purpose. They're usually, you know, existing diesel or gasoline engines that we convert. I think the sort of pioneering work by BMW in this area proved that it's not particularly straightforward. The fuel is very unusual, so you have to accommodate that with some key aspects of engine design. I'd say some of the beyond combustion system requirements. You're also looking at crankcase ventilation and how you deal with hydrogen leaking into the crankcase, and particular attention needs to be paid to the lubricant and how you manage the lubricant and what you do when you get oil droplets into the combustion chamber, which could serve as a very ready pre-ignition trigger for hydrogen. So there are considerations that need to be looked at.
Yeah, I think it's been looked at particularly in heavy duty, where you obviously there's a lot more value in the powertrains.
Yep.
We've got a question from Gerald McMahon and another one on the future of the ICE. So, what would you think that the days of conventional ICE and transmission systems for cars are numbered?
It's certainly a challenging time. I think we see the upcoming emissions legislation, CO2 legislation, getting increasingly challenging, and with the upcoming Euro 7 and extended RDE testing, we see some significant challenges. So we're certainly at a point where it's becoming harder for the IC engine to be significantly more competitive than other technologies. I think the taxation situation in the UK is favouring electric vehicles currently, and there's certainly a definite push from the government at the moment towards electric vehicles. So we're facing a challenging time from the ICE, definitely.
Yeah,
it's really why we're seeing more and more applications coming to market with a level of hybrid support. So that's where you see sort of the mild hybrid applications being the natural stepping point for platforms moving forward.
Okay, we've got probably time for one last question. This is from Claire McAtee, who's asking which second generation biofuels and e-fuels do you see as most promising for the future internal combustion engines?
I think again it's going to depend on market and application.
There's a number of solutions which are being developed at the moment, which are sort of drop into the current infrastructure. Refueling infrastructure, so those naturally become the most near-term promising solutions for those.
Okay, well, I think we're just coming up to time now. So on behalf of the IMechE and the audience, I'd like to thank MAHLE for that really interesting presentation. And as I said, the slides will be available after the event and with the recording of the Q&A session. So thank you again to MAHLE, and at that point I think we can close the webinar.